my talk will address one of the mechanisms that has been discussed a little bit earlier, microstreaming, from a theoretical aspect. Well, my name is Ayache Bouakaz. I'm giving talk on behalf of Doinikov, who was not able to come. And we both work at INSERM research unit, which is also affiliated to the University François Rabelais Tours in France. Well, the subject that we are interested in is the interaction of bubbles and generation of microstreaming in when these bubbles are intonated with an ultrasound wave. As was mentioned in the previous talks, microstreaming is probably involved in a number of medical applications, such as sonothrombolysis or sonoporation. And since with this application we are using a cloud of bubbles or a number of bubbles, so we are interested in looking how microstreaming is affected when we have more than one single bubble. Because current theoretical models, they address this acoustic phenomena by looking only to a single microbubble. So the aim of our work was to develop a model that describes the acoustic microstreaming generated by two interacting bubbles. A model was developed, and then numerical simulations were carried out. And then we looked to the microstreaming when considering a number of parameters. Well, the theoretical approach is described in this slide. So we are assuming that the bubbles undergo linear radial oscillations and translational oscillations in the ultrasound field. One of the hypotheses is that the distance between these two bubbles is much larger than the resting radius of the microbubble. And the approach we have followed is a standard approach. So first, a linear scattered field is computed or calculated, and then this linear solution is substituted into the equations of the acoustic microstreaming. This equation is time-averaged equation of the fluid motion. And as I mentioned earlier, the novelty here is that the acoustic streaming equations are solved for two bubbles. Well, I don't go into the mathematics and the equations that Sasha has developed, because this is too complicated for me. But what we show in this slide with the final equation of the velocity of the acoustic microstreaming is given here, and then the equation of the stress from the acoustic microstreaming is given in this second equation. There are a number of parameters like the amplitude of the incident wave, the initial and the initial radius. So the model was solved numerically. These are some results. This is a first example of two bubbles with the same size, so two equal microbubbles. The point A indicated here is the point where we are doing the calculations. So while considering two bubbles of 1.5 micron in radius, the distance between the two bubbles is 10 times the radius. The resonance frequency of the bubble, in case the second bubble is absent, well, F1 is about 2.8 megahertz. And because of the presence of the second bubble, so the resonance frequency is a little bit lower. And then we are exciting the bubble at the resonance frequency. So these figures show the normalized velocity on the top and the stress in the lower figure. What we can see here is that both the velocity and the stress, well, as expected, they increase significantly when the distance between the bubbles is decreased. So we can see here for different interbubble distances, 10 times, 20 times, and 400 times the bubbles are too large. So it's approaching a situation where we have only a single microbubble. So again, as I mentioned earlier, these bubbles are excited at the resonance frequency. We also calculate the streamlines using this situations of acoustic streaming. So this is the example of these two bubbles with the same size. So the incident wave direction is this way, and we see the streamlines generated here in comparison, for example, to a single microbubble. So there is clear difference in the generated streaming lines in this case. This is another example where the bubbles have the different sizes. So again, we considered two bubbles. One of them has a radius of 1.5 micron, and the second is of 1 micron. These are the resonance frequencies of each microbubble. And again, we show here both the velocity and the stress generated after insulation with ultrasound. So again, the velocity and stress, they increase when the distance between the bubbles is decreased, and again, in this case, again, the driving is performed at the resonance frequency. And similarly, when the distance between the bubbles is too large, so we get a situation which is similar to only a single microbubble. Also, the streamlines are shown here. So the presence of a single bubble modifies the streaming or the stream pattern due probably to phase changes in the bubble radio and translational oscillations. And we know that acoustic streaming is sensitive to this phase change. The model, interestingly, can be used also to calculate or predict the streaming when the bubble is next to a rigid wall or the presence to a wall. Again, here the plots of the velocity. The bubble has a radius of 5 micron, and this is the velocity as estimated for different distances from the bubble to the wall, and the same thing here for the stress. And clearly, the stress, both the stress and velocity, they significantly increase when the bubble is very close to the wall. And experimentally, this data have been reported earlier. So the same way, we look to the streamlines or the stream pattern that is generated by the bubble in the presence of the wall, and we clearly see that the wall affects significantly this streaming or acoustic streaming from the bubble in comparison to if the bubble was at a large distance from the wall. So in conclusion, we have developed the model or theoretical model that allows to predict the acoustic microstreaming. So we can have the streamlines, the acoustic velocity, and the stress generated by two interacting microbubbles. The simulations show that the acoustic microstreaming increases considerably when the distance between the bubbles is reduced, as expected, when these bubbles are driven next to the resonance frequency. And the model can be used also in the case of a bubble oscillating next to a rigid wall. Thank you for your attention.